Okay, so welcome everybody. Welcome to this week's our seminar. Just before Assia begins, I'll just say a few words about housekeeping matters. So the talk is recorded, and you're more than welcome to ask questions during the talk. Assia is very happy to take your questions. If you want to ask a question, you can write to me in chat. So the chat is not active for just normal chatting, but you can write to me. And if you notice something weird, you can also let me know. The other way to ask a question is to raise your hand using the Zoom raise your hand feature under the reactions button. There'll also be a chance to ask questions after the talk, which will also be recorded, but at some point I will stop the recording and you're also welcome to stay after the talk. Assia has also agreed to stay behind and we can have more discussions that go on after the seminar. So I think that's it for as far as the housekeeping goes. So without further ado, it's my great pleasure to welcome Assia Mahboubi, and she will tell us about mathematical structures and dependent type theory. Assia, please go ahead.
Thank you for a kind introduction, and thanks a lot for this invitation. So for those who maybe don't know me, my main scientific interest is in formalizing mathematics, which broadly speaking is about representing mathematics in a fixed formal language. By representing mathematics, I mean defining mathematical objects, statements, proofs. And by fixed formal language, I really mean fixed and very formal language, in particular, so codified that verifying the correctness of proofs can be reduced to a mechanical routine process performed by a mechanical device. So having a language for reducing mathematical truth, mathematical certainty to syntactic rules is maybe as old a dream as the early days of rhetorics. But what makes it a scientific field of its own is the recent combination of two ingredients. And first and foremost, the birth of mathematical logic in the course of the 20th century, which of course made clearer what we mean by fixed formal language. But this ingredient alone was not enough to attract enough attention from researchers in mathematics, as for instance
Assia,
suggested
can
by...
I interrupt you
Yes,
for 1 second?
sure.
I'm getting some comments in the chat that your voice is a bit too soft. Is there any way we can turn up the volume on the mic?
Yeah, let me try. So my mic is at maximum. Is it better?
Oh, that's much louder. Yeah, I think that's
okay.
That's better. Yeah.
So I think there was a problem with my settings. Okay. So this is an excerpt from a quite famous text from the group of mathematicians Nicolas Bourbaki, written in the middle of the 20th century, which opposes the axiomatic method, as they call it, which we could also simply call abstraction, to the logicist approach. And they here explain that they think that reducing the activity of describing mathematics to the precise and mundane description of mathematics in a too formal, a too fine-grained logical formalism would just hide the profound intelligibility of mathematics. But this was written before the second important ingredient I mentioned, which is the confluence, the convergence of proof theory with the theory of programming languages. which gave rise to a flourish of proof assistants, as we can see them on the market today, starting with probably what can be considered as the two pioneers, the Automat system, designed by Nicolas Govert de Bruyne in the middle of the 60s, and the Miser system, designed by Andrei Treblinka and his team shortly after. Both these systems were designed by mathematicians with the ambition of helping users to represent mathematics on computer. But very soon, another community of researchers noticed the interest of these systems for a very specific kind of mathematical proofs, namely correctness proof of programs, which gave rise to a different line of systems, the theorem and LCF systems being the two pioneers of. And these second line of proof systems were systems devoted to program verification and geared towards this specific activity. As of today, the gallery of interactive proof assistants that people can try and use can be broadly divided into two families. The first one is based on a flavor of logic called a higher order logic, hence the name HOL something. And it's the second bullet in my list. And it's a line of provers which can be considered as in the lineage of Milner's LCF pioneer system. And the second family of interactive proof assistants is the one the Cocc, Matita, Agda, Lin belong to. And this family of provers is based on a different flavor of foundations, namely dependent type theory, which can be considered as a descendant of Automat, but also to other foundational works like Martinov's dependent type theory and Girard's work in lambda calculus. As of today, I think it's fair to say that in spite of the original motivations of the designer of Automat and Miser, the largest community of users is interested in applications in program verification. And there's a number of impressive success in this area, and I'm listing only for randomly chosen examples in verified compilators and security-oriented applications. But rather recently, I would say like since the last 15 years or so, a growing interest from a larger and larger community of users with an interest in verifying mathematical proofs can be noticed. So the first two examples on my lists are actually in between the previous list of examples in program verification and mathematics, because these are formal proofs that rely on computation. They're really computational mathematics. And therefore, the verification of the proof includes the verification of a program and its link with other more static parts, more traditional parts of the proofs. The second, the two last examples on my list, by contrast, are really devoted to proofs that are really meant to be read completely and verified completely by hand. There is no superhuman computational power needed here, but the objects that are at stake in these theorems and in these theories are quite sophisticated, and they can combine very different flavors of mathematical theories in such a complex way that perhaps the number of people that are able to understand all the details of these definitions are too few to ensure perfect confidence in the proofs.
Sorry,
anyway,
can I interrupt you for one sec?
Sure.
I'm getting a question in chat from Nikolai Shilov that you didn't mention ACL2. Where do you see ACL2 in the picture of these?
Oh yeah, I did, but it was a bit hidden. So let me go back to my gallery slide. So the THM item here is the first version of the Boyer-Moore line of provers. So it was THM, the first one, then NQTHM, and then ACL2, and all of them were in the Boyer-Moore line of provers.
Mm-hmm. Thank you.
Okay, so no matter which generic instance of proof assistant you take in my gallery, you can roughly describe them under this line. So this scheme here is a core skeleton of an interactive proof assistant. So the very first decision you have to make if you want to craft your own new interactive proof assistant is the choice of the formal logic, the logical foundations you're going to base your system on, and that's my green box on the top. And this will, of course, determine the proof checker, my red box on the right. The proof checker here is modeled after the rules of your logic, and it's here to check by syntactical means that all what you pretend to be a proof is indeed a correct proof. So this red box is really the box that you have to trust in order to trust all the validations that your interactive proof assistant is going to perform, and the trust in your proof checker will extend to all the proofs that have been validated by it. But this choice of formal logic will not only impact the proof checker, it will also impact the way you're going to define your objects, your mathematical definitions and concepts, the things that you're going to describe in your libraries, my orange box at the bottom. And actually, so human users will write, but also read the libraries that you're going to write with the help of your proof assistants. So it's really important here that the language you're using to describe your mathematics, your formalized mathematics here, is as intelligible as possible. Because there is one thing that the proof checker will not check, is that that what you're calling a cat is not a dog. Yeah, there is a matter of trust here that really has to be a human trust. So in order for this to be possible at all, the language used to describe the mathematics in a digital way should be not too far from the communication habits that we have when communicating mathematics on blackboards or on paper. And certainly this language, so close enough to the mathematical practice to be intelligible, will be far away from the level of details the proof checker is requiring. And in order to bridge this gap between almost readable formalized language for mathematics and the formal logic checked by the proof checker, in order to bridge this gap, to perform this compilation-like scheme between my orange box and the assembly-like green box, comes the proof assistance. And without this purple box, which is the proof assistant per se, the activity of formalizing in practice would not be possible at all. So the automation provided by the proof assistant is roughly of two different natures. There's a first nature of automation, which consists in bridging gaps in proofs. So the proofs are so detailed, the proofs validated by the proof checker are so detailed that you have to describe even parts of the proof that are obvious to a human. And so here is an example of something which is maybe not that obvious, but you certainly don't want to do it by hand. It's a silly algebraic identity here. A plus b squared equals, well, what you know. And here is a proof command that I'm using that is provided by my interactive proof assistant so as to automate this proof step. But there is a second nature of automation, which is really important, and it's related to what I've been saying about the intelligibility of formal statements. So here is the definition of the determinant of a square matrix of size n times n, filled with elements in type R. And this is the formula, which is called the Leibniz formula, but whatever. I've reproduced it here, the LaTeX version of this formula. But in the libraries of formalized mathematics that I'm using on a daily basis, it's really defined this way using this code. So this code is not too far from the LaTeX code, which is producing this formula. So this is my notion of readable. But if you think about it, there is still a number of informations that are left implicit here and that the proof assistant has to find out by itself. For instance, by using these capital Greek letters here,
I mean that I'm iterating certain binary operation, here an addition and here a product, but I'm never naming explicitly the operations I have in mind. But it's obvious for the reader that it's the addition and the product attached with, well, a ring structure which endows, well, the carrier of the elements stored in the matrix. I just don't need to make a precise annotation here. It's just obvious for a trained eye. But I have to say something here for the type checker, for the proof checker, for this statement to be just meaningful. So these two different flavors of automations also lead to different techniques in order to be implemented. For the first nature of automation, we're talking here about formal proof producing decision procedures. So I have an identity here and I want to decide it, and I want to obtain a formal proof of this identity if the decision is successful. And so for this nature of automation, the HOL family of prover is probably implementing the state of the art, and has spent a lot of amazing efforts and amazing results in connecting interactive theorem proving with other areas of automated theorem proving, and equipping these decision procedures, efficient ones, with formal proofs of correctness. The second nature of automation here is completely different, and it's here about being able to explain to the interactive theorem prover which abstractions are at stake here, and to reconstruct all the information for the correct instant of an abstraction. And this is what my talk today will be about. So I would like to insist here that the flavor of foundations really play a role here in the way, in the techniques you will have at hand as a user in order to gain this automation. And so what has been observed for the last decade is that dependent type theory, so the foundations implemented by Cocc, Agda, and other systems in my list, have been the most successful in providing a sufficient support at the foundation level in order to make this nature of automation most efficient, which probably explains why the two last items in my list were actually examples of proofs carried in such systems. So before I go further in this talk, I would like to just give you an idea of how important this nature of automation can be. So I will just share a demo. Can you see my Emacs buffer?
Yes.
Mm-hmm. Thanks. So it's not meant to be readable at all. It's just an example of a session of my of the proof assistant I'm the most used to, the Cocc proof assistants. So I'm here doing a mathematical proofs of a so-called Wedderburn's Little theorem, which states that finite integral domain is necessarily commutative, whatever. I'm here describing a candidate proof of this statement, and Cocc is giving me a snapshot of the current state of my proof, where here is the context I have at hand with items like P, a natural number, a hypothesis saying that P is a prime number, and so on and so forth. And this is the formula I should prove under this context at this stage in the proof. Once I'll be done, I will also have to prove another statement, but that will be for later. And so as you can see, I have a certain amount of information here, which is readable as this LaTeX-like approach allows. But now let me show you what the proof checker sees from this context. And here it is. As you can see, things have become much more verbose and bigger. And it's not only because some infix one character notations have become a long qualified name. It's really because a lot of subterms have become explicit that were not printed at all in my previous version. And so I would like to explain you the kind of things which happens between this and that. So let's go back to the slides. Can you see my slides again?
Yep, looking good.
Okay, so as I said, the things that I will tell you are really specific to this dependently typed foundations that I have underlying the proof assistance. So let me give a few words, let me say a few words about the foundations implemented by the Cocc proof assistant, which is so. So these foundations are called dependent type theory. I will not go into the details of the calculus of inductive construction, which is the exact precise version of dependent type theory implemented here. Just think it's a dependently typed lambda calculus. And so here's an extremely brief description of the type system. So it's as usual, lambda calculus with types, and you have the simple types you're hopefully used to, like type variable, type for not that I call n, arrow types like this one. But in this, sorry, in this variant of lambda calculus, types themselves are terms, and the types of types are called sorts or universes. And in Cocc syntax, you will see things like type or prop. I don't want to go into the details of this, but just remember that these are types for types. Then in this type system, you can also have polymorphic type. And what is a polymorphic type? It's a term which has type a sort, arrow, a sort. So for instance, the type of term list is type arrow type. And you can really apply list to an argument, which has to be a type because it's the source, the type at the source of my arrow. So list applied to nat, the type of list of natural numbers, is a type. And so is list applied to nat arrow nat. Now, a bit more exotic than polymorphism, you also have dependent types. And what is a dependent type? It's a type whose type is also an arrow type with a sort as a codomain. But at the source of my arrow, I can now have a data type like nat. So my bool vec here has type nat arrow type. And maybe my intention here is that bool vec is a type of vectors of booleans, because hence the name. And the argument in nat prescribes the length of my vector. So because Cocc is built on the so-called Carey-Howard isomorphism, these dependent types are also used to model predicates. Prime here is also a term of type nat arrow a sort. I've just chosen a different sort, but just don't pay too much attention to that. And so prime is can be used as a predicate to model the primality property on a natural number. So prime applied to 3 is the statement 3 is prime. I can also, of course, combine polymorphism and dependency. My vec here is an arrow type with 2 arguments. The first argument is a polymorphic one. It fixes the type of elements stored in my vector. And the second argument is really a dependent one, which fixes the length of my vector. So vec of bool in 3 is a type of vectors of length 3 and filled with booleans. Okay, so remember we have dependent types. Now the last construction I would like to mention is the one of dependent pairs. So what is a dependent pair? It's data structure allowed in my calculus of inductive construction, where pairs are made of a first element, which have, say, a type A, and a second element, which I've named P A here. And the type of the second component of my pair depends on the value of the first. Okay, so I have a first component here, as usual in a pair, and the type of the second component can depend on the value of the first. So here is an example in Cocc syntax here. Prime nut is the name of my type. With capitals in the name, it's the constructor of pairs. And prime nut is pairing a first component of type nut plus a proof that this first component is prime, which means that I have here a term, p nut p, of type prime applied to my first component. So in this syntax, I'm defining the name of the type, the name of the constructor of the elements of the type, and pnut and pnut_p are so-called projections. So pnut is projecting the pair onto its first component, and pnut_p on its second component. Now I can iterate my pairs so as to obtain dependent tuples, where an element in the tuple has a type which can depend on the values of the other elements stored in the tuple before it. And now, what is a structure? It's just a dependent pair or a dependent tuple whose first component here, the A, is a type. So here is, for instance, a structure for pointed types, types with an inhabitant. It's a dependent pair whose first element is a type because it has type 8 sort. So my small sort here is a type, like nat. And the second component of my dependent pair is, well, a witness that the type is inhabitant, which means bot is an inhabitant of type sort. Okay. So this is a very simple example of structure. Yeah, so just a bit of bibliography here. These telescopes or dependent tuples were already used in automats in the 70s. And as far as I know, the first time someone noticed or wrote the remark that these can be used not only for representing context-independent tuples, but also for structures was Randy Pollock about 20 years ago. So pointed types is a very simple example of structure. Here's a more maybe familiar structure to mathematicians, the one of groups. Groups is a very important algebraic structure for operations that can be combined and reversed, like the operation preserving regular shapes, for instance. So it's composed of datas, a binary low and neutral elements, an inverse on the carrier sets, and some properties about these datas. And let's see how we can represent this in dependent type. So as a dependent type. So here is a structure. It fixes as a first component a type sort, which will be used for the carrier of my group. And then the second component of my dependent pair is, well, the rest of the data and specifications on this data that will endow this carrier type with a structure of group. And the second component itself can be represented as a telescope. This telescope is packing multiplication, inverse, neutral, and proofs that these data have the expected properties. So let's see how we're going to use this representation of structures so as to mimic the implicit information hidden on paper. So for instance, abusing notation, we would write something, casually write something like, let G be a group such that for all small g in G, G times G equal 1. So of course, this is completely understandable, but there's a type error here, right? Here I have a group, which is a package of data, requirements, and so on. And here I'm talking about the carrier of the group, but that's just obvious, okay? We're not going to be pedantic and make this explicit. But for the type checker, there is a problem. And here is how this kind of illusion is implemented. Here's a small lemma. It's so small, I call it a fact, which states that a finite group, which is a group with a finite carrier, always has a carrier with a strictly positive cardinal, because there is at least the neutral element in it. So strictly speaking, G is a finite group, but the notation for the carrier takes a finite set and outputs an element, right? So there is something to be corrected here, and this is the projection. This is the constant which performed the correction of my tuple onto its first component, the carrier, the finite set carrier. And what happened here is that as a user, I input this and I want to read this, but the proof assistant has automatically and silently inserted this. Because I have told my library that I want this behavior to happen, and declaring such constants as as a constant that the system can insert to correct typing mismatch is called coercion mechanism. So let's see another maybe a bit more involved kind of illusion that is current on paper. Now, suppose I have a larger group J and H and K, two subgroups of this finite group, say. Now, it's obvious from the first exercises in group theory that you make as a student that the intersection of H and K, the normalizer of H, the center of H, whatever that means, are themselves finite groups. They're just like very easy first exercise to do. But if I want again to be pedantic, there's a difference between a group construction, which endows this set with a group structure, and just the underlying carrier set. So I'm greasing here the construction of the structure, and this is the underlying carrier set. And the same holds for normalizer and so on and so forth. But again, I will never mention explicitly in any proof that this guy is a group because there is a lemma set thing. So it's just obvious, a canonical construction of groups. So let's see again how we can implement this. Again, same fact that a finite group has a strictly positive cardinal. And I want to apply it to prove that this group, H intersected with a normalizer of K in a context where H and K are known to be finite groups, is a strictly positive natural number. So before I explain in more details how we use this fact on this goal, let me make a brief aparté on a smaller and more easy example. Here is a much simpler context where I have two natural numbers A and B and a hypothesis about a predicate on natural numbers called odd. And I want to use this hypothesis to prove this statement, this particular instance of odd. What I'm going to do is to use a proof command, which is called apply, provided with H, the name of the hypothesis I want to use. And I'm just not going to make the precise instance of H for which value of X and Y I want to apply H. The proof assistant will save me this burden, and it will instead solve a matching equation. So H says that odd of 2 times anything plus anything Y times 2 holds. So I have to find a solution for this unknown X and unknown Y when compared to the term which is under the bar, my current goal, which is this one. And it's an easy problem. This will be my X and 6 will be my Y, and we're good. Of course, matching has no idea about what odd means, and it's a bit silly to name this odd because this is obviously even, but it's just matching and nothing to do with the meaning of and definition of my predicate. Let me make a slightly more involved, pose a slightly more involved problem to the proof assistant. Y has disappeared from odd. I'm replacing here with just 12, and I want to apply H. Here is the new matching problem. The same solution holds for X, but this time it's not clear that it's a solution because it's not clear that 12 matches 6 times 2, right? But in a proof assistant based on dependent type theory, this is really the case because computation, and in particular the computation of the program times, because this is really a program implemented on the type NAT. The program, performing multiplication applied to 6 and 2 really leads to 12, and this kind of equality modulo computation is inside the typing rules of the system. So unification works modulo computation in dependent type theory. So this is not only matching and something much more clever and automated can happen here. But let's go back to our problem here. So our initial problem was to prove this statement using this fact. So we would like to apply this lemma. And if we do so, we're going to have to solve this unification problem where I have restored the G set projections that were not printed. And if I simplify the problem, because by congruence, the unification problem to be solved is G set of an unknown G, which comes from the statement of Cocc GZT0 lemma, should be matched against, well, what's under the bar here? Okay, let's do so. So I have to find an unknown group whose carrier set is this, but this is a human way of phrasing the problem. For unification, unification doesn't know about groups or anything, just like it doesn't know about odd, and there is in general no solution to this problem. Except that as trained readers, we know that there is a canonical construction of groups which will lead to these carrier set, provided that A1 and A2 themselves are grouped. What is nice is that I can phrase this as a canonical solution to a unification problem, saying that if I want to solve this problem when the intersection is not between arbitrary sets, but between projection of groups, I can take X as this canonical solution of, so this intersection here is greased here. It's not exactly the same as this one. And I can use this canonical solution in my unification algorithm and pursue. So this was my original problem. I take H as G1. Oh, for G2 doesn't work exactly because here I don't have a G set as a head symbol, but an N. So let's create another variable and pose another unification problem. And so in order to go on, I need to solve this unification equation, which has no solution in general, but there is one in my library because there is a canonical construction of group involved. I can phrase it as a canonical unification solution, teach it to my unification algorithm, and I'm done. And then from this problem, I apply my lemma and I'm done. Okay? So this is called a first class type class algorithm. And there's this prologue-like search of instances, which happens in unification. So as far as I know, the first time someone noticed it could be the case with the Mokran Saibi in the late 90s. Unfortunately, I think he didn't realize the full potential of this idea. And it's only available in his manuscript written in French. So it took 10 years to be rediscovered by people. I think the first were people from the Matrices system, but two papers appeared about at the same time, implementing it either at the level of unification or at the level of...
When you were saying the name of the algorithm, your internet connection broke up, at least for me. Can you just repeat the name of the algorithm?
Of which algorithm?
This extended unification.
Oh, unification hints.
Hints.
Hints, yeah, as in the title of this paper.
Right, okay.
So the hints are these canonical solutions that you're, this database of canonical solution to unification problems otherwise unsolvable that you're storing in a certain database known to the unification algorithm, and then you have to like make unification interact with it. And the algorithm is really described in both these papers.
Mm-hmm, thanks.
Yeah. Okay, so so far so good. Here are examples of usage of applications of this idea. I think I have about 10 minutes left. No, 5 minutes left, right?
Yeah, maybe like 6 or 7.
Okay. So maybe I will skip that example and focus on this demo. Can you see my Emacs?
Yes.
Okay. So I will play a little bit with matrices. So matrices are a bit like the vectors I had given as examples of dependent types, but except that there are 2 dimensions instead of 1. So it's matrix is a dependent type. Oops, sorry. Which has one polymorphic parameter. So if I have an arbitrary t and I apply matrix to t, I get a type which has these two dependent parameters, nat and nat, for the size. And please read this as type sort. Okay, I can apply it to t. I can apply it to int, a type for integers. It gives a term of the same type. And so if I assume I have two terms, u and v, which are matrices filled with elements in t and size t times 2, then can I multiply my two matrices by the term u star v? No, I can't. And of course I can't. What would be the multiplication here? T is completely arbitrary. But now if A and B are matrices of size 2 times 2 filled with integers, then A times B makes sense. And you can see that Cocc has found some annotations here. It says that yes, A times B is a matrix filled with integers. Okay, so let's see a bit more examples of usage of this infix multiplication symbol. I'm assuming x and y are integers, p1 and p2 are polynomials with integer coefficients. The same infix notation times can be used to multiply integers, to multiply polynomials. It's in fact attached to instances of a ring structure and not really to a precise data type. Okay, I'm not only sharing the notations here, I'm sharing also the theory. So if I take integers here, I can prove this silly lemma, which is just a ring identity, p minus p times q equals 0. I'm rewriting simple properties of rings, and I'm done. And if I replace my ints by matrices, of course, the same proof will hold. Okay, same here, a silly identity on integers, proved using properties of ring, and whoops, sorry. I'm replacing integers by matrices, and it doesn't work. And of course it shouldn't, because here I'm using a commutativity of the multiplication. And of course it was able to infer that there is an instance of commutative ring for integers, but there shouldn't be one for matrices, of course, right? Okay. So the crucial ingredient here was really these first type classes, but also the fact that behind this infix notation here, the multiplication that I've been using, for instance, what is hidden is a projection onto the appropriate component of my dependent tuple, here the data for the multiplication operation, which is applied to x and y, the arguments that are surrounding my infix notation. But the dependent tuple, the projection is performed on, is left unknown here. And it's the unification or type inference algorithm, which will infer which multiplication to take from the carrier type, which is given by x and y. If x and y are ints, then it will find an instance of ring for integers, which stores, among other things, the multiplication, and the multiplication will be retrieved by this constant. So really here, I'm inputting terms with holes, big holes, and it's only the unification or type inference which will make the term as complete as need be for the type checker to accept it. Okay, so I hope I can finish in 2 minutes. I've been talking about the representation of structures, but of course you have to organize these structures into hierarchies in order to take benefit of the sharing and inheritance relations between them. And all these relations in the big DAG of structures are implemented using the coercion and instance declaration that we have been. It's a bit of a subtle art, and it's actually an active topic of research to represent as faithfully hierarchies, and most of all to control the complexity of proof search in this graph of structure. But there is a substantial literature that you can have a look at if you're interested. Now, the last point, and this is my last slide, a realistic example of things that can go wrong is this one. Suppose I want to model a structure for norm modules. So these are just a vector space with a norm, and of topological space, which are spaces where you can have, well, topology. A norm module are in actually topological space because of the norm, whatever that means. And you know that products of topological space are themselves topological space, just like for groups, right? Okay, but also products of norm modules are norm modules. And there's a standard way of building that. Now, for all these good reasons, products of norm modules are themselves clearly topological spaces, right? So by the same kind of machinery that we've used for groups, I should be able to do this. I have a hypothesis saying that a certain predicate P holds for all balls centered at V, a guy which lives in a norm module. And I want to use this hypothesis to show that P holds for a certain ball where the center lives in, well, a product of norm module, W times W. And if I do things too naively, this will fail for this reason, because I have two competing paths to go from norm modules times norm module to topological space. One says that the product of two norm module is norm module and then downgrade it to a topological space. Or else I can downgrade both my norm modules and then use the product topology. And these two competing paths are not equal modular computation, just like 12 was equal to 6 times 2. And so the prover has no way to infer that these are equivalent paths. This problem is actually, there's a nice example of this problem with a more intricate mathematical object, but it's really what happens. In the paper about formalizing perfectoid spaces, the last example in my list of application in mathematics. And there is an explanation of how this problem can be fixed in a recent paper published last year. So to conclude, we've seen that with the help of interactive theorem provers, we can model the axiomatic method, which is advocated by Bourbaki, and all the benefits of lightening mathematical prose and exhibiting the mathematical structures that are factorizing notation and theory rights in the literature. The solution relies on open terms hidden by notation plus enhanced type inference and unification. There's a lot of subtle things actually to be done right in order for this to work in practice, from complexity to design of dependent records. It's I mean, it's not as easy as just saying this is the solution, but unfortunately this allows to cover the mathematical structures used by Bourbaki, but not more, and we could hope for more in the future. It's not there yet. And in particular, there's one thing I have not talked about is morphisms between structures. This is a bit more complicated a problem, and I hope that in the near future we could automate proofs by naturality in the same way as we have made proofs by canonical construction in this talk. But for the moment, this is still an open question as far as I know. Thanks a lot.
Thank you for this amazing talk. I loved it. So we have plenty of time for questions. Please put up your hand using the Zoom hand up feature if you would like a question. Andy, go ahead. I think you should be able to unmute yourself. Oh no, hang on, one sec. Okay, try to unmute yourself.
Yeah, yep. Thanks. Yeah, thanks, Assia. Very interesting talk.
Thank you.
Just a quick question. For the things that you've been talking about, is that and the current state of the art, right, are Lean and Cocc about the same, or is one better than the other in this respect?
That's a very good question. So I would say they're about the same. So they're exploring different strategies. If I can go back, yeah. So Zal said, so the main ingredient is this idea of using dependent record as first-class type classes by enhancing inference algorithms that are implemented in proof assistance. Both Lean and Cocc and implement the two ways that are described on the slide by enhancing unifications, which is the examples I have been detailing, and by enhancing type inference, which I have not been detailing, but which is another different approach for implementing first-class type classes. Now, the differences in the libraries. One thing is the feature provided by the proof assistants. Another is the way the libraries will use these features. So all what I've been explaining is really depending on how groups are defined, how coercions are set, how unification hints are added, and it's really at the interface between the choices of design of the proof assistant and the choices of design of the authors of the libraries. So here is where the difference is. The largest libraries of formalized mathematics in based on enhanced unification, as opposed to the choice made in mathlib's lean library, which is based on type inference. I hope this answers your question, but I mean,
that's great. Just a supplemental, and my impression is that Agda is behind the game of both Cocc and Lean in this respect. Is that correct? I mean, it doesn't quite do things in this way.
I'm sorry, I missed, I think, one word. Could you?
So I just I get the impression that Agda is lagging behind Cocc and Lean in with respect to the things that you're talking about. Is that correct, or is that a misimpression?
I'm not familiar enough with Agda, I think. I know there's a type class algorithm, a type class mechanism in Agda. I think it belongs to the second flavor. I'm not sure there is unification hints in Agda. And if I'm correct, then it should be possible to do the same in Agda.
I see. Okay, thanks. Okay, thank you.
I'm sorry not to be more precise.
Paul Taylor, please go ahead. You can try to unmute yourself.
Okay, well, thank you for a nice talk. Now, I should say, before I make my comment, I am a categorist, but I'm not trying to divert your talk. And I am aware that categorical ideas mix very badly with recursive ones and proof search and that kind of thing. But so my observation is you were talking about intersection of subgroups.
Right.
Now, that's a familiar situation that in categorical jargon is called that we say that the forgetful function from groups or in any kind of algebras to sets creates pullbacks.
Okay, yeah.
Now that much jargon probably doesn't help you. What I'm thinking is that by keeping as an eye, shall we say, on how categorists would describe the situation, I wonder whether there is some benefit you can get in the methodology or the strategy of designing your proof search software so for example, I mean, you would make the same observation about rings or you know, lots of other structures, and merely from a software engineering point of view, you wouldn't want to repeat the same thing for each of these structures independently. So I wonder whether taking advantage of the way that categorists would put it, you can better design your proof search algorithms.
Yeah, that's an excellent question, and I'm afraid I don't have a fully satisfying answer. The whole point of that game is to transpose the automation, which is made like completely self-evident with the elementary lemmas available in category theory, to transpose them as algorithms in the type inference or the unification or all the algorithms that are implemented at the level of an interactive proof assistant. that probably means understanding better how to represent categories in dependent type theory right, which I don't really have a right answer at the moment. Maybe one thing I can say that is that one point which would be really interesting would be, for instance, from an proof engineering point of view, would be to be able, for instance, to take into account for initiality, for instance. So there's something which is really not satisfying from my point of view, which is that, for instance, we know that polynomial expressions or polynomials are an initial in the category of rings, for instance. And this is certainly something which is used to implement automation for instances of rings. So for instance, if you want to decide an equality in an instance of ring, you will, well, just forget about the details, read the polynomial from an expression in the ring, normalize it, compare two normal forms, and so on. And you're doing this in a very ad hoc way, and in a very ad hoc way for every category. And there is certainly something like a free theorem or something connected with free theorems from parametricity to be understood here. But really, I don't know. I just don't know for the moment. So this kind of papers are trying to scratch the surface of it. But for the moment, I'm afraid I don't have anything satisfactory to say about that. But thanks for this question.
Okay, I think we have time for one more question. So Timothy Griffin.
Yeah, thanks, Assia, for the interesting talk.
Thank you.
You mentioned the term canonical structure several times, and could you just explain what you mean by that and what are the details?
Yeah. So first, it's a misnomer, which is due to this author Omicron Sabi. So let me try to find my So this author was the one who coined the canonical structure wording. It's a misnomer because it should really be canonical instances of structure. And so I'm sorry, I might have used it because it's in the Cocc, it's named this way in the Cocc syntax, but I try to avoid it as much as possible. So in Cocc specific vocabulary, and I really mean Cocc syntax, a canonical structure should be understood as a canonical instance of a structure. So for instance, here, I'm going to, let's take the example of intersection. I'm going to define what a structure of group is and prove the theorem which says that if I have two arbitrary instances of group, I can define a third group which has as carrier the set intersection of the carrier of the two arguments. And then I will provide all the necessary proofs that this intersection is endowed with all the necessary properties for it to be a proper instance of my formal definition of what a group is. Then this is not enough for my unification algorithm to be aware that this equation has a canonical solution. I have to tag my theorem, my construction of a third group from the intersection of two first ones. I have to tag it, and the syntax for this will be canonical structure. But as again, I'm repeating for the third time, this is a misnomer. It should really be, this is a canonical instance of the structure of group. So canonical structure in Cocc syntax is really a synonym for unification heads. Is this answering your question?
Yes, thank you.
So just maybe a last sentence. In Cocc, the only canonical solution to unification problems that you can add are based on these dependent tuples, hence the name, canonical instance of structures. the mechanism which is described in this paper is a bit more general, because there is no reason why you should restrict to dependent tuples. So you can add more equations of this kind where G set is not necessarily a projection of a dependent tuple.
Thanks a lot, Assia. So as the last thing before I stop the recording, I asked everyone to unmute, and we can give Assia a round of applause to thank her for her talk. Stop the recording now, and